Alright, now that we've gone through the DICOM imaging format, we're ready to start with the nifty imaging format, which is a way to look at objects as 3D images in R and with other neuroimaging software. nifty stands for Neuroimaging Information's Technology Initiative. It's a standard representation of images, and it's the most common used type of analytic file. These files have been developed to facilitate cross-platform and cross-software interpretability. These images are three-dimensional arrays, so they're stacks of the individual slices that we saw on the DICOM images. A way to think about this is we can think of a DICOM as a single sheet of paper, and we can think of a nifty as a stack of papers or as a book. In this table, we're going to do a comparison of the DICOM and the nifty formats to get us used to the differences between the two. In the first row, we have the file extension for both of the files. So for the DICOM, these have a .dcm extension, and for the nifty, we have a .nii or a .nii.gz extension, where the gz extension is for gzipping the file or compressing it, which we'll go over in just a minute. The file representation for a DICOM is one slice of the brain, so we saw that extensively in the last lecture. For the nifty, we have a 3D image of the entire brain, or a three-dimensional array of numbers. In the DICOM, the header contains many fields and has protected health information as well as hospital-related metadata. In contrast, the header for the nifty doesn't contain patient information, but it does have the imaging metadata, such as the pixel dimension that we looked at in the last lesson. The DICOM storage is a bit different, what we saw in the first lecture, where each one of the DICOM images for a subject is stored in an individual file. For nifty, since we only have one image for each file, we can store these all together for one subject and a single folder. As we were saying before, doing analysis on nifty images is much easier than on DICOM, but one problem is that hospitals tend to have DICOM saved on their packs, or if you get them directly off the scanner, they're going to be in a DICOM format. So the first thing we're going to go over is how to convert images from a DICOM format to a nifty format. And lucky for us, there's already an R package that does this, the oro.dicom package. We're going to use the function DICOM to nifty to convert these files. The DICOM to nifty produces a nifty R object, and when we save this R object, we get something with a .nii or a .nii.gz extension. Alright, so you'll remember in the last lecture we read in multiple DICOM files to create kind of this list of our 3D image. So we'll have you go ahead and rerun the things that we did in that lecture off of this slide so that we can convert this DICOM image into a nifty image. So once you've done that, we can go ahead and we can use the DICOM to nifty function. So we can take that list, all slices T1, and put that into DICOM to nifty, and then we're going to save the output from that as NII_T1. So if we look at the dimension of NII_T1, we see that this is 512 by 512 by 22. So now we have 22 slices together for our image. And then if we look at the class of this object, before we had lists, but now we have something of a class nifty. And if we go ahead and plot this, it looks the same as it did last time. But here we're plotting the 11th slice of our array. So you see we have NII_T1, and then we bracket, comma, comma, 11, which picks out the 11th slice. There's a package that's created for working with nifty files called oro.nifty, and this has a function called write nifty and read nifty, which we're going to use to write NII objects and to read these into R to do analysis. One thing to note is that the default for write nifty is to save nifty files in a compressed format, so it'll save everything automatically with a .nii.gz. Okay, so let's work with the oro.nifty package. So we're going to go library oro.nifty to load the package in. And now let's set our working directory to neurohacking data nr/brainx/nifty. So now what we're going to do is we're going to save this file that we converted from a DICOM to a nifty in this folder. So we're going to create a file name. We picked output 3D file, and we saved that as that string as the variable f name. Now if we use the write nifty function, what we need to do is pass in a nifty object, which will be called the argument nim. So we say nim is equal to the name of our nifty file, in this case nii_t1, and then we assign the file name. So we say file name is equal to the name that we wish, which is saved in the variable f name. And so now we've gone ahead and written out that nifty file. Let's go and see if that's in the folder that we wanted. So we can use the R function list files to check and see if that file is there. So we're going to use list files. We're going to use our current working directory, which we can get using getwd. And then we're going to look for something that matches the pattern of our file name, which is pattern equals output 3D file. And then we see that we have this file in that folder, and that it has a .nii.gz extension. We can also see what other files are in there. If we do list files, getwd, and then we use a pattern t, we see that we have a t1 and a t2 in this file as well. And we're going to go ahead and read in the t2 using the read nifty function, also part of the oro.nifty package. So we'll say nii_t2 is equal to, so we're assigning this as the output of read nifty. And all you need to do there is put the file name, and then we don't normally reorient the images because we've had some trouble using that function from the read nifty. The dimension of this is the same as the T1, so it's 512 by 512 by 22. Okay, I promised earlier that we would talk about the compressed image files and why this is important. When you have a compressed file, it'll have the extension .nii.gz. And the reason you do this is it's good for saving disk space, and it also makes reading and writing the files much faster. Another great thing is that you can move files from one location to another much more quickly when they have been compressed. It's excellent for scripting and analysis of large imaging populations. But if you don't want to zip your files, you can just use the write nifty function and pass in the argument gzipped equals false. Okay, for those people who don't want to use R to convert their DICOM images to nifty images, you can use the program DCM to NII, and we have a citation for that at the bottom of the page, and this is part of the MRI Crom platform. Basically, this will convert a set of DICOM images to nifty files, and it's great because it can handle multiple formats and file types. But for this course, we're going to focus on R, so we put more emphasis on that. Okay, we also mentioned at the beginning of the course a few other file formats. We're not going to go into as much detail about these file formats, but we'd like to mention them here because they do come up when you're working with data. The PAR-REC files are files from a Philips scanner. So files that are subjects that are scanned on a Philips scanner will have a PAR-REC file as opposed to a DICOM file. There's software called R2A, which can be used to convert PAR-REC files to nifty files, and we have a link to that down at the bottom. There's also analyze files, and these are what nifty files were originally based on, but they have a separate header and image, and so the nifty files kind of are an improvement on that because there's only one file that you need to deal with. Then we have the nearly raw raster data, or the NRRD, which is another less common format, but most imaging software can read NRRD.